Welcome back to Physics 142 Online. We're going to introduce today a very powerful technique for calculating electric fields, especially when we have symmetrical charge distributions. The basic point is that Coulomb's law has the physics that we can use to calculate the electric field of any charge distribution. And in particular, if we don't mind coding this into a computer, we can easily take any charge distribution, break it down into small pieces, find the field that each piece produces, and then add them all up. But sometimes the vector algebra that's necessary to do that is pretty complicated. However, when we've got charge distributions that have high symmetry, we can take the physics in Coulomb's law and express it in a different way that makes the calculation of these electric fields very easy. And we can do things that would have taken a lot more work using Coulomb's law very quickly. So that's what Gauss's law is useful for. But first, in order to understand what Gauss's law is telling us, we've got to define a new quantity called the electric flux, or phi. In some textbooks use phi sub e because later on in the course we will also define something called magnetic flux. But for now, phi represents flux. And it's a quantitative measure of the number of electric field lines that pass through a given surface. So here's an example. This gray shaded surface, a rectangular box, imagine that it has surface area A on the two parallel surfaces to the right and to the left, and it's got a uniform electric field E passing through the box. So the field lines go in on the left and emerge on the right. So if these electric field lines are perpendicular to those planar surfaces, then phi, the flux, is simply the electric field magnitude times the surface area of those two surfaces. We do make a distinction between field lines that go into a surface when there's a closed surface involved and field lines that come out. So when field lines come out, we assign that a positive charge and we say that that's a positive flux. When field lines go in, we say that that's a negative flux. So keep that sign convention in mind as we go through this part of the course. Now, you might have situations where the electric field lines are not oriented normal to the planar surface, but at some angle. And so what we can do here, imagine this wedge where we still have a uniform field, so field lines E are all parallel and they come in through the planar surface and then they emerge through the planar surface that's tilted at an angle theta with respect to that normal direction. So theta is the direction from the horizontal to the surface normal. And we know for sure that the flux coming in through the vertical planar surface is the same as the flux coming out because the number of field lines is the same. And that means that we can write down the flux through surface 1, which is just E times A, and set that equal to the flux through 2. So the flux through 2 must therefore, if it's going to be the same as E times A1, which is that surface area on the left, it's got to be equal to E times A2 times the cosine of theta. A2 is a larger area, right, because that wedge has a longer surface, but if you take A2 and multiply by cos theta, you just get back A1. And so here the general case for flux is that it's the electric field magnitude times the surface area times the cosine of this angle defined in this way. So using vector notation, we use a dot product to express this definition. So the electric field when there's the electric flux when there's a uniform electric field and there's a planar surface is just E dot into the area vector. And here we are using a definition where we say that the area vector for any surface is equal to the magnitude of that A times n hat, which is the surface normal vector. And of course this definition only works when you have a planar surface so that the normal vector is the same everywhere on the surface. Now, what about the general case? Even more general is where we might have a surface that is undulating, that's not planar, and where we might have an electric field that has a different magnitude and a different direction at different points on the surface. So what if we wanted to calculate the flux for a surface like this? It's far more complicated, but we just use the basic strategy familiar to us in calculus, where we take the entire surface area and carve it up in little pieces that we will call delta A sub I, each of those little squares will have its own surface normal vector n sub I, and then the electric field passing through the surface at that point is in the E sub I direction with magnitude E sub I. So the amount of the flux passing through this surface component, surface element, delta A, is just vector E dotted into this area vector, right, which is magnitude delta A times n hat. So this is how much flux there is through that small surface element. We can take that in the limit where delta A becomes very, very small. We'll call it dA, and then we will call the flux contribution d phi. So expressed in this way, all we have to do in order to get the total flux through the entire surface is to integrate. So the total phi is the integral over the surface of this quantity E dot n hat times dA. And using that definition that was presented on the previous page, we can define a differential surface vector dA, which has a magnitude equal to the area of the element, and then it has a direction equal to the surface normal n hat. Some books write this as E dot n hat dA, some write it as E dot dA, but they mean the same thing, and the integral is over the surface. And I think you'll agree that in a case like this, this could be a very complicated integral to solve, and we might indeed have to do it numerically. But when we have special kinds of surfaces and special symmetries for the electric field lines, this kind of an integral can actually be very easy to calculate. And most of the cases where we use Gauss's law, that will turn out to be the case. These integrals will be very easy to do. I might mention, though, before we go any further, that the word flux comes from the Latin word that means flow. And so if you're having a hard time grasping what we mean by flux, think of these field lines as representing a flow of something. Imagine that you had water flowing through a pipe. A flux was originally developed to describe something like that. Electric field lines don't really tell us that there's a motion of anything, but they do suggest a certain type of flow. Now, let's look at some qualitative examples of electric flux, because this will help us understand where Gauss's law comes from. Imagine that we have this closed surface, this gray surface, so it's a closed surface, sort of a balloon-like surface, and inside of it there's both a plus and a minus charge, and they have equal magnitudes. So this is a dipole, and we recognize the field lines emanating outward from the positive charge going inward toward the negative charge, and we see that if we wanted to calculate the flux through that closed surface, every field line that goes out through the surface, and that means positive flux, has a negative contribution for the field lines coming in. And so that means for every field line coming out, it also goes back in, so whatever flux there is outward is canceled by the inward flux, and therefore the net flux through that closed surface is zero. Remember, flux is a measure of the number of field lines passing through the surface, and direction matters. How about this case? Here we have a case where there's a dipole, but it's a non-symmetrical dipole, and so there's a plus 2q and then a minus q. And if we look at this, we see some of the field lines that go out also come back in, but an equal number that come out don't go back in. So this is a case where there's a net flux because some of the field lines go off to infinity and don't come back in through the surface. This means the flux is positive. We've defined flux to be positive when it's in the outward direction coming out of a closed surface. And then here's another case. What if the charge is actually not inside the closed surface? So imagine this cube, gray shaded cube, and there's a positive charge outside of it. Look at this. Every field line that goes into that surface also will come out of that surface. No matter how we draw the field lines, that's just the way it works. And so this too is a surface that has a flux of 0 through it. Doesn't mean there's no field lines, it just means that every field line that goes in also comes out. So notice what's going on here. If we look at these three cases, we can see that the flux through a closed surface is related to how much charge is inside the surface. On the far left, the net charge inside the surface is 0, the flux is 0. Same thing on the far right. The net flux is 0 and the net charge inside is 0. In the middle, there is a net charge inside and the net flux is not zero. So what we see just by inspection of these cases, there's a connection between the amount of charge inside a closed surface and the net electric flux through that surface. The quantitative statement that relates those two quantities is called Gauss's law, and let's see where it comes from. Here finally, or here's the answer. We'll show you what the answer looks like and then show you where it comes from. So the phi through a closed surface, when we have a closed surface, we indicate that on the surface integral by putting a circle on the integral sign. That means the surface that we're integrating over is a closed one. So one way to write that is E dot n hat dA, the other way is E dot dA, and that's the way that I will normally write that in class. So, but it's not just any old surface integral, it's an integral over a closed surface. And the statement that is Gauss's law says that that is equal to 4 pi times the Coulomb constant times the net charge enclosed by the surface. And using a different constant, epsilon 0, which has the same value as 1 over 4 pi k, we can write this a little more compactly. This is the way in physics we write Gauss's law more often because it gets rid of this factor of 4 pi that we would prefer not to have to carry around in our equations. So the flux through a closed surface is equal to the net charge enclosed by the surface, the net charge inside, divided by this constant, epsilon 0. Now, where does it come from? I'm not going to give you a general derivation, but I will show you how this emerges from a special case. Imagine that we have a spherical surface of radius r that is centered on a positive point charge plus q. So we want to evaluate the flux through that surface due to the point charge on the inside. And we know an expression for the electric field, a distance r away from a point charge. It's kq over that distance squared. And it's always radially outward from the point charge. And this symmetry will allow us to calculate the flux integral very easily. So the flux, we know, is the integral over the surface of this quantity E dot dA. Well, dA is a vector that has magnitude dA and then direction in the radial direction outward, which happens to be the same direction as the field line. And that relationship, the parallel relationship between the field line and the dA vector, is true everywhere on the surface. That's the symmetry that I'm talking about. So everywhere on the surface, the E dot dA vector can simply be written E times dA times the cosine of 0, because E and dA are parallel. So the E dot dA that's inside the integral simply becomes E times dA, and we know what the E is for points on the surface of the sphere. So phi now integral E times dA. Notice there's no more vector signs because we've evaluated the dot product for this simple case, and now we just have to plug in for E, kq over r squared, and then multiply by dA. Well, before we do the integral, realize that k and q and the radius r are all constants. So they come outside the integral, kq over r squared. Integral dA, well, what does this mean? The integral is a sum. dA is the surface area element. So if we add all of those up over the entire surface, we just get the total surface area, which is 4 pi r squared for a sphere. So the result for phi is simply phi is equal to 4 pi times the Coulomb constant times q, which was the point charge inside, and that's the same as q over epsilon 0. So this agrees with the statement of Gauss's law given above, so long as we realize that the q that's in this equation is the total charge inside the closed surface. So what does Gauss's law do for us? For high symmetry charge distributions, like a point charge, right, we can quickly use Gauss's law to calculate the electric field in regions around the distribution. And so in order to convince you of that and show you the utility, we're going to have to do some examples, and that will occupy our time in class. I hope this has been a good introduction. I'll see you.